be
So
discussing today?
mostly uh, on I'll start with probe current and probe size, how they are related and what are the parameters needed to be used and how we can change them, and then I'll touch upon factors affecting interaction volume, then how image formation is happening in SCM and how we'll interpret them, and what are EDS and WDS. So moving forward, so to recapitulate, there were three important parameters which were considered uh, for obtaining good resolved image, and those are effect of aperture size. Like we have to control the aperture such that we will get a best optimum probe size so that our resolution will be better. Then working distance, again we need a proper working distance so that our we can get a optimum spot size. Like if we increase the working distance, then we have seen the spot size being increased because of decrease in the convergence angle, and that degrades the resolution. So we need to optimize this working distance as well. And third, condenser lens strength. So this also, if by increasing the condenser lens strength, we will be able to reduce the probe size, and which will eventually help us getting the better resolution. So in order to get this probe size, we need to manipulate this probe current. What and so the probe, and that can be done by this simple relation, like the probe current is related to probe size by this formula. IP is probe current, dg is probe diameter, and alpha is convergence angle. So one thing we can do here is, like, either we can increase the probe diameter by increasing the probe current. Like if by increasing the probe current, then our probe diameter is going to increase. And also, if let's say we keep this probe diameter constant, then there is only one variable remaining, that is convergence angle. So by increasing the probe current, we can increase this convergence angle. So this relation is quite important. Then moving on, the next question comes, like, what happens when a beam electrode encounters specimen atoms, like when So as we know, like by selecting properly the operating parameters for SEM electron guns, we can manipulate the aperture and the characteristic of the focused beam, which reaches our specimen surface, and eventually we are able to control the energy, diameter and beam current and convergence angle of the same. So at in normal SCMs, they are present at very high vacuum. So the whatever the residual atomic density is there, it is very low, and the beam electrons are highly unlikely to encounter any atoms uh, uh, passing along the flight of path. So that's why it is always we have seen like the column of SAM is always maintained at very high vacuum, because so that the electrons is flowing, it will pass unhindered. So what are the uh, things that electron encounters when it hits the uh, specimen? It it goes through two type of scattering. One is elastic scattering and one is inelastic scattering. So this inelastic scattering basically refers to a process where the energy of the beam electron is reduced, that is transferred to the specific atom when they interact with them, and this whatever the energy is lost, they include the ejection of weakly bound outer shell atomic electron, and and they form the secondary electron, and when they eject a tightly bound inner shell atomic electron, then we call them as characteristic X-rays. um, or that those electron can be de-accelerated, and those produces the continuum X-rays, which we also call Bremsstrahlung X-ray or braking radiation. We also get other type of things like we may get a plasmons, which are nothing but waves in free electron gas, or we may get heating of the specimen, which we generally uh, signify as a phonon. And when the energy is lost in this inelastic scattering, the beam electron only deviate very slightly from the path, and uh, this inelastic scattering when happens, then it is given by a equation d by ds, the minus 7.85 z rho by ae ln 1.166 E, where E is the beam energy and Z is the atomic number, and A is the atomic weight, and there is a J term here, which is mean ionization potential. Uh, this is also referred to as very famous equation called Bethe equation. And what does it tell us? It tells us the rate of change of loss. Tells Bethe equation tells us that rate of energy loss, that is dE by ds, increases as the electron energy decreases and increases with the atomic number of target. This we can see as this dE by d is directly proportional to z, that is the atomic number, and is log. When this is decreasing, then this value will increase. If this E will decrease, then eventually this will increase. Then after this inelastic scattering, elastic scattering also occurs when the beam electron is deflected by electric field of atom, uh, causing the beam electron to deviate from whatever path it's traveling. So that whatever the probability of electric scattering will happen, that depends on the nuclear range of the atoms from which it is being deflected. And let's say electron is deflected by electric field of an atom, the electron found at a point P1, and it is being deflected by an angle phi. Then this deflection can happen over a cone, and this if this electron will get deflected here, then it can fall in any of the point in this region, and so the cross section of this cone is given by, from the elastic scattering, given by 1.62 into 10 to the power minus 20 Z square by E square cot square 50 by 2, where here 50 is threshold elastic scattering angle, and here the elastic scattering causes the beam electron to deviate out of a very small angular range of incident trajectory, which we call as convergence of incident beam, and they are controlled by the electron optics. So this is very important to know how after elastic scattering the electron is traversing its path. So when as we have seen, like whatever electron is coming, it is interacting with the surface of the specimen at a particular volume. So it is important, like what are the factors. It depends on uh, like when it interacts with the volume. So the question need to be addressed when an electron is hitting at a certain volume. So how does the interaction volume changes with the mm, atomic number, which is also, we can say, it tells us about the composition of the material. Change of interaction volume with composition, or we may say atomic number. The when the atomic number of the target increases, denoted as Z, when the atomic number of the target increases, the dimension of interaction volume decreases. And also the atomic number have different kind of a shape of the interaction volume. Let's say we have low atomic number, then it looks kind of like pear shaped, and when we have high atomic number, then it is more of scattered, or we may say hemispherical. Now change of interaction volume with incident beam energy. Uh, the shape of the interaction volume is relatively independent of the beam energy, but the size does matter, and it increases with increase in the beam energy. So we may say shape of interaction volume remains unchanged. but its size increases with increase in incident beam energy. And the third dependence of interaction volume is change of interaction volume with tilt of the specimen when the tilt angle increases, the beam approaches very closer to the surface, and it changes the volume drastically. So as the tilt angle increases, the maximum penetration of beam is reduced. So when I say tilt angle increases, maximum penetration of beam is reduced. Now moving on to some SEM instrumentation, that like after the beam hits the specimen, then there is elastic or inelastic scattering. Then whatever outcome it will be detected by some kind of detectors. So let's talk about detectors now. So in SEM, uh, two output would majorly see, that is backscattered electron or secondary electrons. So some of the properties which are important from this backscattered electron and secondary electron, so that it is possible to design a detector, and those are uh, properties for making one detector. One is abundance, that is the total yield per incident beam of electron of whatever backscattered electron or secondary electron is there. This is sensitive to specimen properties such as average atomic number, chemical states, and what are the crystallographic orientation or local magnetic field. But the total electron signal is not measured by the detectors, rather the counts of it. And the next point is angular distribution. So knowing the trajectory of this uh, backscattered electron and secondary electron after leaving the specimen is very important, where this detector should be placed so that it will intercept the signal. So for a beam incident perpendicular to the surface, uh, backscattered electron or secondary electron, whichever are emitted, they follow certain kind of functions, like it may be a cosine or sine function. So the relative abundance along any direction is proportional to this whatever angle between this surface normal and the direction it is propagating. And the third property which is important is kinetic energy response. Backscattered electron and the secondary electron, they have very significantly different kinetic energies. Backscattered electron retains a significant fraction of incident energy of beam electron from wherever they are coming out, and only 50% of the backscattered electron escapes. But the secondary electron are much lower in kinetic energy, which we have already seen. It is less than 50 electron volt and greater than 50 electron volt for backscattered electron. So this secondary electron exits the specimen with less than 10 electron volt, and the kinetic energy distribution comes around in between 2 to 5 electron volts. So what type of detectors we normally see are one passive detectors. Now what are these? These are uh, scintillation based detectors and semiconductor charge deposition based detectors. And as the large fraction of backscattered electron are emitted from specimen with energy greater than 550 electron volt, so they can be detected with a passive detector. So these include scintillation detectors and semiconductor charge deposition based detector. What is the scintillation detector? Uh, so when um electrons strike optically active material, they cause emission of light. So the optical materials, those are selected, they produce high signal response that decays very rapidly, which enables high bandwidth operation. So the emitted whatever emitted light is there, it is collected and passed by total internal reflection, and they are multiplied. Whatever signal we are getting, they are multiplied with using a photo multiplier, and they are converted into signal, and we detect those signals. So we may say scintillator detectors comprises of optically active materials. And second one is semiconductor charge deposition by detector. Like certain semiconductor devices, they can detect energetic electron that penetrate into active region of devices, where they undergoes elastic scattering. So when there is energy deposition in this semiconductor, they uh, they provide enough energy to the loosely bound valence shell electron into the conduction band, and because of this there is a potential difference uh, happens. And whatever free electron are passed on to the conduction band, they can be collected at the surface electrode, and they are measured basically. So here, like, we provide enough potential bias and collect electron which are measured. And these are all for backscattered electrons. These detectors are for backscattered electrons, and for secondary electrons, for secondary electrons there are a number of detectors present. I will only talk about one of the detectors, and that is Everhart Horner detector. They are also called secondary electron detectors. So what it does is, whatever secondary electrons are coming, they increase the kinetic energy of low-lying electrons to a sufficient energy level so that they can penetrate through a thin metallic layers uh, that is applied to discharge insulating scintillators. This Everhart Thornley detector, they can detect all kind of secondary electrons like the Se1, Se2, Se3. This Se1, which are generated within the uh, directly, like whatever primary beam is coming directly under it on, and they can detect that also. Now after detectors, we will go to the image formation. Like after the electron source, the beam follows a central optical axis of the lens system and is sequentially defined by different apertures and that focused by the electromagnetic field of the lens system. So there are scanning coils here. So within the final lens, this scanning coils acts to displace the beam of the optic axis so that it can be addressed to a location on the specimen. Uh, so at any particular time there is only one ray path uh, through the scanning system, and the beam reaches only one location on the specimen. The SEM image, uh, whatever is formed, those are created, those are analyzed and created in any computer screen, and those tells us about the discrete xy location on the specimen, and measures the effect of interaction of beam with the specimen at each location. So for a single grayscale SEM image, this interaction could be output from a single electron detector, such as that ET detector which we talked about. ET detector, they are also called single electron detector. So it is also possible to measure the output from more than one detector simultaneously. So when that is done, the multiple grayscale SEM images are built up at the same time during the scan. So it is essential to realize that even when these multiple signals are being collected simultaneously, and multiple images are produced, only one scan is needed, and whatever different acquisition are done, parallel acquisition, uh, they are not uh, they, they, they are not detected actually. So whatever image we are getting, they are not the true image, as uh, we are recording it and afterwards we are seeing it. So in this SCM, at each location sampled by incident electron beam, each signal is measured with appropriate detector, and then the analog whatever measurement is done, analog measurement is converted to a digital one, and the beam XY location and the intensity of the signal that generate a digital stream of data, which we note down, and we plot it in terms of uh, like intensity versus whatever electron energy we are giving. So how this scanning action is done? So we have beam locations on specimen, which we also call specimen pixel. So this here an area with equal edge dimension, like whatever there in our specimen is copied into the computer screen with different dimension, and the way it is translated, it's given by the magnification, that is the ratio of each dimension of the specimen area and the display area. This is the specimen area, the display area. Now whatever information we are getting in SM image is conveyed when a contrast in the backscattered or the secondary electron signals is created, and those are created, this contrast is created by differences in the interaction of beam electron between a specimen feature and its surrounding. So this contrast can be uh, conveyed in different manner conveyed by different manner. There can be number effect, where it refers to contrast which arises as a result of different number of electrons leaving the specimen at different beam location in response to changes in specimen characteristics at that particular location. Refers to contrast which arises as a result of different number of electrons leaving the specimen at different beam location in response to change in specimen characteristic at that location. Next, contrast can be conveyed by trajectory effect, that is, it refers to the contrast resulting from differences in the whatever the path that electron takes after leaving the specimen. Refers to contrast resulting from electron taking path after leaving the specimen. Third, energy effect. So here the contrast is carried by a certain portion of backscattered electron distribution, like whatever it may be backscatter electron secondary electron distribution. So uh, so this tells us about this gives information about the distribution, gives information about distribution of either BS backscatter electron or secondary electron. So for example, the high energy backscattered electron, they are helpful in imaging specimen uh, like as we have seen, different atomic number, mm, they have different, that scattered differently, and they have different notion in backscattered electrons, and that's why they also give crystallographic contrast too. And the secondary electrons, which are low energy electrons, they escape from the shallow region and they give the surface information. So we may say this energy effect, this BSC giving atomic number information or crystallographic information, and this secondary electron gives surface information. So while considering the microstructures, so how we interpret this SEM images? So there are different contrasts are present, such as atomic number contrast or surface specimen topography contrast. They are interpreted in different ways. So the atomic number contrast which are appearing for like let's say like the Eberhard Thornley detector which we talked about, they usually gives information about the secondary electron, and when they capture these SC1 signals, they also capture backscattered electrons which are directly emitted into the solid angle. uh, Whatever these backscattered electrons which are detected in Eberhard Thornley detector, they gives information about this SC2 and SC3 electrons. So though the SC1 signals of ET detector doesn't show much variation, but the backscattered electron component of Eberhard Thornley detectors signal reveal the atomic contrast. So we may say this semiconductor detectors and this ET detector, for these two, uh, higher atomic number region appear brighter than lower atomic number region. So while imaging the topographic feature of specimen, uh, topographic contrast has several components that are coming from both backscattered electron and secondary electrons. So like atomic contrast for interpreting the specimen topography, is backscattered electron coefficient shows strong dependence on the surface inclination. uh, Strong dependence on surface inclination, and because of this we get different contrast on the surface. And backscattering from a surface perpendicular to beam is directional and follows uh, sine or cosine function, and this contribute a trajectory component to the contrast. This contribute a number component to contrast. So whatever backscattered electron is coming directly perpendicular to beam is directional and symmetric about the beam and provides trajectory component to the contrast. Provides trajectory and if there will be any tilting, they become highly directional and asymmetrical, and those surfaces form a center for forward scattering. This again provides trajectory component too. So if electron falling on any tilt, they also provide trajectory component to the contrast. And these are all for like backscattered electron. And for secondary electron, they strongly depend on surface inclination. They also strongly depend on surface inclination, and they increases rapidly as the beam approaches this grazing angle, and this also contributes a number component to the contrast. Increases rapidly as beam approaches uh, grazing incidence, and this provide a number component to contrast. So while imaging with this Everhard Horner detector, a finely focused electron beam, when they pass sequentially through a series of location on the specimen, a mixture of backscattered and secondary electrons signals are uh, emitted, and this different type of shapes and shades provide different contrast to the specimen surface. With this ET detectors, when they are compared with uh, optical, like our eyes, like they are also sort of detectors only. So when they are compared, so what are the different comparisons can be made with the ET detector and human eye? Are like the human eye have a very sharp defined line of sight, which is matched by the electron beam. Uh, they also provide a narrow cone angle of rays, so the observer of SEM image is effectively looking along the beam, and whatever the beam is striking, and whatever the illumination is coming from the outside by sun rays, they consist of direct component and an indirect component. So for ET detector, when there is a let's say give a positive biasing to it, there is a direct signal component, uh, uh, which are backscattered electron emitted by the specimen, and that those are defined by the scintillators, and the indirect component, uh, which are AC3s, which are collected from the specimens, and those are diffuse illuminations. When we consider whatever the lights reflected by the object through the sun, which may compare. So different optical parameters, uh, electrical optical parameters uh, gives a lot of basic features of electron beam in a scanning electron microscope after it emerges from the final aperture of objective lens and before it impacts the sample surface. While changes to the beam inside the electron gun and inside the electron column are also important to us, thorough understanding of beam in the chamber is very necessary. So for that we need to know about the beam energy, beam diameter, beam current, and so we need to know about beam energy, beam diameter, beam current, then beam current density, beam convergence angle, beam solid angle, then optical brightness, the focus. We need to have information of all of this. So first talk about the beam energy. One of the fundamental parameter is the energy of the electrons in the beam. So this parameter represents the initial energy of the electron as they enter the SEM chamber. So beam energy has a direct effect on many important aspects of SEM operation, such as the size of the excitation volume. It's a very important parameter. Size of excitation volume and the intensity of X-rays emitted. So it is very necessary to choose a parameter carefully and set it to appropriate value. So frequently the beam energy is used as several thousand electron volt or higher. So ACMs are capable of generating electron beam up to 30 kilo electron volt. So why this kilo electron volt? So we know the electron volt as a unit of energy, uh, but we are using it in as a measure of voltage. So this electron volt related to the method used by SCM to impart energy to the electrons that emerge from electron source. The electrons are accelerated from a low energy to high energy using an electrostatic potential difference generated by high voltage power supply. So the negatively charged electrons are repelled from the surface with negative electrical potential and attracted to surface with positive potential, and the potential difference is measured in volts. 1 electron volt is simply the energy acquired by an electron when it is accelerated through a potential difference of 1 volt. So similarly, we can correlate with other like 20 kV, we can add as 20 kV and such. So this underlying connection between the accelerating voltage used by the microscope and the resulting energy beam can help make sense in different terminology used in SCM regarding the beam energy. So on many microscope we set the accelerating voltage as, let's say, 30 kV. If you want to work in high energy, and if you want to work at low voltage also, we can use 1 kV. And the usage of this energy and voltage as vice versa, like we can use alternatively this electron volt and keV and kV alternatively. So aside from this, there are other things like, depending on the technology used by the microscope, the electron in microscope may change energy more than once during the path from electron source to surface. So some microscope uh, want to improve imaging performance by modifying the electron's energy uh, while present in the optical column. So in many microscope it is possible to do so by deaccelerating the electron beam. It decreases the beam energy just before the electron emerges from the objective lens. Similarly, we can increase the energy of the electron. The term used to describe the electron beam energy at the point of impact on the sample surface is called landing energy. The physics of beam specimen interaction depends only on the landing energy of the electron and not on their energy at points in the optical path. That's why we can change the energy of the electron in the optical path, and it will not change the information it will give us. So the critical important phenomena are the size of excitation volume in specimen, the number of characteristic X-ray peaks available for use in compositional measurement, or the high energy limit of continuum X-rays are all function of this landing energy. Of these detectors, two spectroscopic technique which were discussed, uh, not broadly, just some points, basic points. Those will consider WDS and EDS, that is energy dispersive X-ray spectroscopy. First, let us consider EDS. And this EDS can detect X-rays uh, from all elements uh, for atomic number greater than 4. Why we are using this energy dispersive X-ray spectroscopy? They can detect X-rays for materials having Z greater than 4, and the main advantage of EDS is the speed with which it collects the data, mm, and it is also very portable. Let's say advantages of EDS is high speed data collection, portable, and ease of integration with pre-existing system. What are the disadvantages? The resolution is very bad. And they have very low peak to background ratio, because uh, they cannot because of the high background signal coming from the Bremsstrahlung radiation, and they interfere with the data in of whatever data is provided by the EDS. The next, WDS, it is wavelength dispersive X-ray spectroscopy. As the name suggests, they use one or more diffracting crystals whose independent spacing is already known, and they for the calculation they use the Bragg's law. So what are the main advantages we can say it is having over uh, energy dispersive spectroscopy? They have better resolution, over better resolution, a better peak to background capability to detect small smaller amount of elements, and it can also detect elements having atomic number less than 4 also, and there is no artifact in the spectrum from the detection and the signal processing, because it very nicely differentiate signal to noise ratio. Next, coming to the questions, to obtain higher convergence angle, we need a larger aperture or a lower working distance, because if we have a high working distance, then the convergence angle becomes higher, and as a result we know the probe size increases and we don't get a better result. So for higher convergence angle we need a lower working distance and a larger final aperture size. So for in SCM, for better resolution, we need to keep the probe size. We need to decrease the probe size so that we can uh, see a very small uh, specimen having like dimension in the order of nanometer. So the probe size needed to be smaller. So which one among the following statement is false when working distance is increased in an SCM operation? When working distance is increased, then we know that the resolution degrades, probe size becomes bigger, so what are the options here? It gives less magnification, degrades the resolution. It is correct. It is also correct. It produces largest profile, correct. Reduces scan length, no. So which one of the following is false? So doesn't have to do anything with scan length, so yeah, this is the correct answer. As the interaction volume increases, the spatial resolution increases. What information can be obtained from the brighter region in backscattered electron images? So it indicates the element with higher atomic number, because with higher atomic number they provide nice contrast with the background, and higher atomic number regions seems to be brighter in backscattered electron images. So with decrease in glancing angle of incidence, the secondary electron and the backscattered electron yields increases. Okay, this is assertion which is taken, and for that the reason is more scattering occurs closer to the surface as the glancing angle of incidence, like more the light is coming near to the surface of the uh, specimen, that is basically we are reducing the angle of incidence. So then more scattering is happening at the surface, and because of that we may say the yield of secondary electron backscattering electron is increasing. So this first statement, with a decrease in glancing angle of incidence, the secondary electron backscatter electron yields increases, is a correct statement, and more scattering occurs closer to the surface as the glancing angle of incidence. This statement is also correct, and this is the reason for this statement, like as uh, the electron is more closer to the surface, then more scattering will be happening closer to the surface, and hence the yield of secondary electron backscatter electron increase. So both the assertion and reason are true, and the reason is correct explanation of the assertion. This will be the correct option. Which of the following statement about atomic number increases is correct? With increase in atomic number, as we know, atomic number we consider most of the time backscattered electron. The electron yield for first option is electron yield for backscattered electron is greater than that of secondary electron. That seems correct. The electron yield for secondary electron is greater than that of backscattered electron. It has nothing to do with atomic number in case of secondary electron, and the electron yield for backscattered electron and secondary electron remains the same. No change in atomic number. Electron yield for backscattered electron always changes. No yield for backscattered electron as well as secondary. It's incorrect. So the correct option will be the yield for backscattered electron is greater than that of secondary electron. As the electron beam penetrates deeper into the specimen, inelastic scattering increases. More deeper and deeper it will go into the specimen, more it will interact with the specimen, and more energy it will lose. So the inelastic scattering increases more inside the specimen. In elemental analysis in SEM, which of the following technique would you like to achieve more resolved data? And now only we just see, like, WDS is way better than this energy dispersive spectroscopy because this provide better resolution. So in elemental analysis we will use WDS because this secondary electron imaging, that will give us the surface information, and backscatter electron, this will give us the crystallographic information, not the elemental information of the specimens. Only this EDS and WDS will give us the elemental information, and WDS will give better information than this EDS. So the correct answer will be wavelength dispersive spectroscopy. Is secondary electron image gives surface information. This backscatter gives crystallographic information. Or about the atomic number of element being there, and these two will give elemental information, and from that WDS will give better information than EDS. The spot size at the specimen grows as the working distance is increase. We know the spot size increases and resolution degrades. So the correct answer will be larger. Which of the following mode of operation do you prefer for SEM analysis of biological samples? For biological sample, we will use environmental SEM because there we have to prepare the sample beforehand accordingly, so that whatever, like in normal SEM there is something called charging effect that will degrade the biological sample pretty fast, degrades biological sample pretty fast, and they are also not conducting, so we have to like through plasma treatment we have to coat it with conducting material, then we will see it. So in such processing, better we should use environmental SCM. Like here for biological sample we do plasma treatment for SCM analysis and coat with conducting metal so that we can do SCM analysis. Magnification in a scanning electron microscope depends on the excitation of magnification. The scanning coils, as I have seen in our slide, the scanning coil helps in distributing the electron over the specimen, and they scans the sample totally and resolve the specimen, and hence helps in magnification. The trajectory for backscattered electrons and secondary electron in SEM: straight and curve respectively, curve and straight. And for backscattered electron the trajectory should be straight, and for secondary electron it should be curved. So the answer will be this one, straight and curved respectively, because these are very high energetic electrons, greater than 50 electron volt, but these are low energetic electrons, and that's why they deviate from the path and they follow a curved path. But here as they are high energetic, they can follow a straight line path. As the condenser strength increases, the probe size decreases. As the condenser strength increases also, we can say the probe current increases and the probe size decreases, which eventually results in better resolution. Probe size decrease, because with decrease in probe size we can easily resolve very smaller specimens. Which of the following factors contribute to the contrast measurement? as I have already seen, for contrast measurement, this number component, trajectory component, energy component. Like number component, as we are having different number of collection of electrons from different part of the specimen, they provide different uh, values, and hence they provide number component. The trajectory component is at because of different surfaces, as the electron hit the surface at different angle. They have different uh, symmetries. If hitting the surface perpendicularly, they are symmetrical, and if they are not, they are hitting the surface at an angle, they are asymmetrical, and they provide different information to the they provide different counts to the detector, and hence different information about the specimen. And those are the trajectory components of for the contrast, and hence the different angles have different contrast with respect to the background. And energy component, as we have discussed, backscattered electrons uh, have uh, higher energy, so because of that they can easily tell give information about uh, the atomic number, because different element having different atomic number, if they are probed with high energy electrons, then they will provide the different contrast. And also for different crystallographic orientation also, if the high energy electrons interact with different orientation, they will also provide different contrast. In this way, energy is providing different contrast to the specimen. And for as we already know, for the lower energy electrons, as they interact with the surface, they provide the surface information, and those we already know, those are the secondary electrons. So in this way, all of this number component, trajectory component, and energy provide contrast to the material. But this is it for this week, and we will meet next week. Thank you.